Okay, in this last uh, use of the derivative for the week, we're going to see how the derivative can help us with rational functions, and especially in sketching their curve. Remember, a rational function is a function of the form that y is equal to some expression that has a function f of x and a function g of x, and we're told that g of x cannot equal 0. Well, for us to go about doing the graphs, it's going to involve uh, determining basically three different pieces of information. First, we're going to need to find the asymptotes: horizontal, vertical, or oblique. Secondly, we'll want to find out the stationary points. And classify them. And thirdly, we want to find the axes intercepts. Now we've done all these things individually at some point during your math career. Now we're just going to put them together. And we're going to basically have three different types of rationals we're going to look at. The first type is where we have a linear over a quadratic. Second type will be a quadratic over another quadratic. And the third type will be a quadratic over linear. And there are many more rational functions beyond these, but these give us the basic idea. Notice in the middle one, they're both quadratic, so they both have the same degree. In the first one, the top is linear, the bottom is quadratic, so the numerator has a degree that's smaller. And in the last one, we have a quadratic degree 2 over degree 1. We have a larger degree on top. So even though there are many other types of rational functions, this gives us the three types of relationships we can have with their degree. Remember to find any vertical asymptotes. You always set the denominator equal to 0. To find any horizontal asymptotes, we have to do a limit as h approaches 0, as x approaches infinity. Let me change that. Let's say the absolute value of infinity of our linear function, of our rational function, we'll call r of x. And the same thing would be used if we're going to do a oblique, and it turns out to be an oblique asymptote. Oblique means just not horizontal or vertical, a slanted line or curve or some other function that we approach the behavior of as x approaches infinity. Now on the first type, let's number the types 1, 2, and 3. So on the first type, the limit as x approaches infinity of the type 1 problems, where the numerator has a lower degree than the denominator, this limit's always going to be 0. And so y equals 0 is going to be our asymptote. You know, as an example, if we have x over x squared, very simple. That reduces to 1 over x. And that approaches 0 as x gets very large. On the second type, where we have a quadratic over a quadratic, let's say r of x equals 2x squared minus 3x plus 5 over x squared plus 4x plus 3. If we take the limit of this, here's the pen is acting up even though it's been charged the entire night. I'm going to divide everything by x squared, so it's going to be 2, not plus, minus. Minus 3 over x plus 5 over x squared, and that's 1 plus 4 over x. X's are not 5's. Plus 3 over x squared. In that limit, as x approaches infinity, the two constants stay constant, and 3 over x, 5 over x squared are approaching 0 as their denominator keeps getting larger. So here the asymptote is y equals 2. A situation of where we might have an oblique asymptote, especially in the third situation there. So let's say we have y equals 3x cubed plus x squared minus 1 over x minus 2. Alright, I can't divide everything by x squared because my denominator would approach 0, and this is x cubed. So what we're going to do is perform the basic division. I'm going to rename this. So we're going to take x minus 2 and we're going to divide into 3x cubed plus x squared minus 1, leaving a space for the x term because we really have 0 x's. Let's go and start out at 3x squared. 3x squared times x is 3x cubed. 3x squared times negative 2 is negative 6x squared. When we subtract, we get 7x squared. Then we bring down that 0x. X is going to be 7x. 7x times x is 7x squared. 7x times negative 2 is negative 14x. Subtract, we get 14x. Bring down the minus 1. Now we have a plus 14. So we have 14x squared, 14x, minus 28. And that gives us 27. So this expression is equal to 3x squared. For that rational function, 3x squared plus 8x plus 14 plus the remainder of 27 over x minus 2. Notice, as x approaches infinity, this last part is approaching 0. 27 over x minus 2 is approaching 0. So our function is going to behave the same way as this one, as x gets larger and larger. So if we were to go to Desmos and we were to type in our original function and type in this function, as we zoom out and make x grow larger and larger, the graph of our original and the graph of this restatement of the original are going to be pretty much the same. Now the other things for you to pick up through this particular section, since my pen is acting up a little bit, if you look at examples 10, 11, and 12, starting on page 643, you will see how to find the asymptotes. First derivative, you're of course going to have to use the quotient rule because you have a rational function. And again, how to use the derivative? Well, we want the derivative to be 0, so only concern ourselves about the numerator, setting up your sign diagram and interpreting, and how to find the x and y intercepts. Once you've looked at those examples and studied those, you can be very brave and go on and work 21E, question 2C, from number 3, letter B and D, and then from number 4, letter A, and letter E. And those will be your work for Monday. Make sure you turn in your special problem set today. I will be by sometime this weekend to pick up all the papers, clean up the room as needed, etc. Thanks for all your hard work I know you've done this week. See you on Monday.